Welcome back. In this section, we're going to talk a little bit more specifically about some examples. And also, it will be our first chance to look at how different algorithms perform. And it will give us an idea of the fact that things are subtle. Things take a little bit of thought, and I hope that this will motivate us for what comes afterwards when we look at details of different algorithms and details of how they perform. So once again, this course is about these two lines here at the center. I want to minimize a function f of x. Remember that x here is a vector. For us, because I want to be able to draw these examples for you, I'm going to use n equals 2 in this lecture. Then I'm going to give a few specific examples of f. Now, the course, as I've mentioned, is going to cover a number of different types of functions. And one of the biggest class of functions that we'll be interested in is what's known in machine learning and statistics as M-estimators. Examples of M-estimators include just simple least squares regression, what's called ridge regression or L2 regularized regression, lasso, logistic, and so on. I'm going to focus on these three, tell you what they are, and we'll give a first crack at seeing how different algorithms perform. So let's talk about ridge regression first of all. Ridge regression comes from the simple problem of trying to fit up a line to a set of points. So given data, x and y, x1, y1, x2, y2, and so on, I want to find a linear relationship between x and y. Now, I have to make a general note here that typical terminology and notation in optimization is sometimes at odds with typical notation that is used in machine learning and statistics. And you've already seen this. All of a sudden, you're saying, wait a second, I thought x was the parameters that we're trying to choose, and now I'm telling you that x is data. So this is something that is frustrating perhaps, but we just have to deal with it, and it's better to get used to it sooner rather than later. So x, and you'll have to infer this from the context as well. So x in this case represents data, and what I'm about to write is beta is going to be the parameters we're optimizing over. So the linear relationship between x and y that I want to find is going to be of the form y is approximately x transpose beta. What ridge regression tries to do is it tries to solve the problem of finding such a beta that fits all of these data as closely as possible. So let's write down an optimization problem here. So what I want to do is I want to minimize 1 over n. N is the number of points, so this represents the average loss. The sum, I equals 1 to n, of xi transpose beta. This is the fit that I'm trying to find, and I'm going to compare it to the actual data point. Now, if I stop here, this is what's called the ordinary least squares problem. So I'm trying to find a beta in order to match my data x and y in a linear way, and I'm trying to do so in a way that minimizes the sum of the squared errors. But this isn't ridge regression. Ridge regression adds one additional twist, which also says, let's also try to balance this error on the data points with the sum of squares of the coefficients of beta. So here, let me use an index j here, so it's not confusing with the I, which runs over the data points. So j is going to run from 1 to the dimension of beta, the number of parameters we have. Again, you see this is another common change in notation. In optimization, oftentimes we'll use n to denote the number of parameters. In machine learning statistics, very common to see n as the number of data points and d or p as the number of parameters that we have. So this is the problem called ridge regression, and there's a number of reasons that we might want to solve this instead of ordinary least squares. This isn't a class about statistics, but I'll just briefly mention that if you have nearly collinear columns in your regression problem, this is a very common type of thing to do. It's one way to balance bias and variance in the linear regression setting. So this is the problem that I want to solve. Another way I can write this using some norm notation, I'd like to minimize 1 over n times the norm of x beta minus y squared plus lambda times the Euclidean norm of beta. So this is again an optimization over beta, and to write this exactly in the notation we had before, this is subject to beta living in the set of all d-dimensional vectors. So there's really no restrictions in this case on what beta has to be. So this is my optimization problem. How do we solve it? We're going to talk in this course about several different classes of algorithms. One very representative element of the first class is called gradient descent. We'll look at a number of variants of gradient descent. And Newton's method is another class of algorithms that is a representative of another class of algorithms that we're going to discuss. So ridge regression, again, is the problem of f of beta is equal to 1 over n times x beta minus y squared plus lambda times beta squared. What does gradient descent do? Well, it says initialize at some beta 0. You could even pick this randomly. You could pick this as the origin. In some cases, the initialization is important, and we'll talk about that when we come to it. But in general, we can think about initialization as being just any random initial guess. How do we update it is the central question that we care about. The gradient descent update tells us that once we've run this update for t steps, we're at beta t. How do we get beta t plus 1? Beta t plus 1 is equal to where we were before plus an update. We'll talk about what all of this means and where it comes from as well. But for now, rather than telling you where this comes from, let me briefly tell you what this means. So this is where we are now, where we are after t iterations. Eta is my step size. Sometimes in machine learning applications of optimization, it's also called the learning rate. And this is the gradient. We'll have an opportunity to talk in more detail about what a gradient is, but you can think about it as basically just the vector of all first derivatives. And what it represents is the direction that locally, infinitesimally, looks the steepest. So this is just saying update beta by taking a small step in the direction where things look most promising. Very natural algorithm. Newton's method is a little bit more complicated, a little bit more sophisticated, but looks very similar to this. We again initialize at some beta 0. And the Newton update says beta t plus 1 is equal to beta t minus eta times the Hessian of f, this is the second derivative, inverse, times the gradient of f beta. So what's the only difference between the Newton update and the gradient descent update is that I pre-multiply my direction, the direction that I move in, the direction of locally steepest descent, by this matrix. Again, this is called the inverse Hessian matrix. So again, we're going to talk in detail about these algorithms, but I just want to actually show you how they perform. All right, let's have a look and see these models in action so we can get an idea about how these trajectories evolve over time. So first we're going to try gradient descent with a small step size. So clicking play here, what do we see? Well, first thing is that it doesn't even make it to the optimal solution. That's one thing we should notice. But still looking more locally here at the line, you'll see that it's moving perpendicular to the contour lines. This is exactly what gradient descent promises that it will do. It looks locally what is the best decision, and it follows it. And this is what this line is doing. We should also note that the decision that's best locally in this particular problem is also not the best globally. That initial direction that it's following is not really the straightest path or the shortest path to the optimal solution. Let's scroll down a little bit and contrast that to what Newton's method does. So it looks like Newton's method does something different. Rather than going perpendicularly to the contour lines, it's actually in this case tracing a beeline for the optimal solution. It's taking the shortest path basically and doing much better. Let's try to increase the step size and see if that gives us something different. So we can see here, let me pause it so we can look at the trajectory. You can see that gradient descent in this case, I've taken a larger step size. It's not as smooth as it was before, but it has some things going for it. First of all, it makes it to the optimal solution. So that's good. Also, we can see that, again, its performance is exactly as promised by the description of gradient descent. It's going perpendicularly to the contour lines. That's what gradient descent does, but it's taking much bigger step size. So you see it's producing this zigzag that wasn't present before. So let's just see that one more time in action here. Okay, so this is gradient descent with a somewhat bigger step size. Let's see what Newton's method does with a bigger step size. I need to pause it here, otherwise you won't even get to see it. It's so fast. Boom, right away. Almost looks like one step. We can't even tell exactly what's happening. Okay, so extremely fast. It gets to the optimal solution following exactly the same trajectory as before, and it gets there right away and then it hangs out. Let's try one last experiment before we go back to the slides, which is let's increase the step size even more and see what gradient descent has to say. So, and now we see a completely different behavior than what we had before. First of all, it's important to remark that, again, gradient descent is doing exactly what it's designed to do. The gradient is pointing perpendicular to the contour lines, and it's taking a step size in that direction, but we've told it to take quite a big of a step size. And we see in this case, not only is there a zigzag, but actually there's a complete failure to converge. Let's turn back to the slides now and discuss these things a little bit more in detail. So this is taking a larger step size. So what happens? If we zoom in here and you look carefully, again, it's moving, the trajectory of gradient descent is moving perpendicular to the contours. This is what it's supposed to do. But you can see here that the step size is much larger. So we no longer have the smooth convergence. On the other hand, of course, it's faster. This is what we should expect. We're taking a larger step size, we're moving faster towards the optimal solution. But on the other hand, it looks like we're doing all of this unnecessary zigzagging. So this is definitely potential inefficiency of gradient descent. The next panel over, so again, this is gradient descent with a large step size, with a larger step size. And this is Newton. Newton, again, is tracing basically a direct line for the optimal solution. Now, I should note that Newton is not always going to magically find its way directly toward the optimal solution. This problem has some particular structure, namely it's a quadratic, and this is why Newton's is doing this. But again, it's moving much more quickly and directly for the optimal solution. So a natural thought here is, well, gradient descent seemed to do better. When I increase the step size, let's increase it even more. So let's do that to see what could potentially happen. Maybe it will converge even faster. But we see that something undesirable all of a sudden happens. So again, this is gradient descent with a much larger, and in particular, too large step size. So what happens? So first of all, again, note that the behavior of gradient descent is exactly as advertised. At every point, it's moving perpendicular to the contour lines. But we can see here that we don't even have convergence. In fact, not only does it fail to converge, it actually diverges. So the questions that we should be asking here are, first of all, what is the difference? What accounts for the difference between gradient descent and Newton? You saw that it's not just that one is faster. They're actually doing very different things. They're moving in different directions. We should also ask, this is a little bit of an easier question to answer, which is why would anyone use gradient descent when we have Newton? So this is something that is worth thinking about. There's a computational answer here. And if you look back at the formulation of Newton, my hint for now is think about the complexity of every single iteration. So it will be instructive for you to look back at the definition of gradient descent in Newton. Of course, we're going to come back and talk about this in great detail, but it will give a hint. Now, but more pressing here, we saw that with very small step size, looks like we didn't even converge at all with a number of iterations. With slightly bigger step size, we converged more quickly, and then with even bigger step size, we diverged. So this is a little bit sensitive. We don't want to solve our problems by just randomly guessing these step size parameters, trying again and again and again and again. Even though these are very simple two-dimensional problems that are very easy to compute, very fast to compute, what should be motivating us is the setting of problems that are really massive in scale. And so we don't want to be running them again and again and just approaching them with an ad hoc way. What if one parameter size doesn't converge? Do I just randomly try something else? So I'll just summarize that entire discussion by saying, what is the correct or best step size? Is there a way for us to know this? Is this an answer that we can give? Okay, let's move to a next problem, which is again a regression problem, but a little bit different from ridge regression. So lasso is similar in that, again, I want to find a linear relationship between x and y in my data. So I have x1, y1 up to xn, yn. This is just as before. I want to find an approximate linear relationship that's defined by parameter beta. So I want to find beta that gives x beta approximately equal to y. And so I have a cost function that has, again, two parts. One, which tells me how well does my beta fit my n data points. And then I have a different penalty. And my penalty here will not be the sum of squares of the beta i's, but it will be the sum of the absolute values of the beta i's. And more compactly, I could write this as, very similarly to what we did for ridge regression, minimize 1 over n x beta minus y squared plus lambda times now the 1 norm of beta. So why would we do this? What's the difference in terms of the beta that's produced of lasso or L1 regularized regression? This is called the L1 norm, hence the creative name. Why would I want to solve this? So we'll see again with more developed examples that we don't use this when we have nearly collinear columns as we might use ridge regression, but this is actually a very important tool when beta has many entries which are zeros. This is a very useful and powerful application formulation when we believe that beta is sparse or nearly sparse. So what does that mean? This means that many entries of beta, of course we don't know which ones, are 0 or close to 0. So this has been a very important problem, very important formulation that sometimes is called sparse regression, sometimes it's called compressed sensing or compressive sensing, and it will be a main motivation for us when we develop a number of different tools, a number of different algorithms. So it turns out that for lasso, let me again copy down that problem from the previous page. So I want to minimize 1 over n times x beta minus y squared plus, remember that this term here is the sum of absolute values. So it has this point. The absolute value of, say, beta 1, what does this look like? It's this function here. It has a point. And because it has this point, it's not differentiable. And in particular, there's no Hessian. If it has no first derivative, it certainly doesn't have a second derivative. Which means no Hessian. So Newton's method, which seemed to do so well for us in the previous example, is completely out here. We're not going to use that. We need something a little bit more sophisticated here, even more sophisticated than gradient descent, because we don't even have a gradient. But it turns out that we have something very close to that, which is called the subgradient method. I'm not going to define this in detail because it takes a little bit more motivation and development of notation. But what we're going to compare here is the subgradient method, which is very similar in spirit to gradient descent. And another method called the proximal gradient method. And we're going to cover both of these in more detail. So let's have a look at the trajectories and see how they compare. So you can see here on the left, this is the gradient-like method. So this is subgradient method. And what you can see here at the end is that it's not even converging. It's actually seems to be going around and around the solution, whereas the proximal gradient method is converging much more quickly and directly to the point. So let's turn to the computer now and just have a look at what those trajectories each look like. Okay, so clicking play here, this is the subgradient method, and you can kind of see how that line forms, that initially it's doing pretty well, but then at the end it seems to get stuck in some kind of limit cycle. So it's not actually converging to the point. A few other things that you should notice is that we're no longer moving directly perpendicular to the contour lines anymore. So this is in fact something that's a little bit different than gradient descent. You can also see that the contours themselves look different than they did in the previous examples, because this is no longer a quadratic function. So this is a function that has corners and sharp points, and the contours themselves show that. So now let's look at proximal gradient. And you can see how quickly it converged. So if you just look at even the slider in this little movie, it just takes a few iterations for this to converge right away. There's absolutely no cycling or anything else. So proximal gradient descent works, is going to be our algorithm of choice here. And this example and the importance of this kind of L1 regularized regression is going to be a key motivation for us to develop proximal point methods. So let's turn back to the iPad now. And just summarize the points here, which are, we'd like to know why does the subgradient method cycle at the end? Naturally, can we fix that? And more vaguely, but I hope more intriguingly, you're asking yourself, what is this mystery proximal gradient method? And where can I learn more? So just to wrap up this particular session, this class is going to cover exactly these types of algorithms. We're going to look at things like gradient descent and variance of gradient descent. We're going to look at Newton's method and variance of Newton's method, approximation to Newton's method. We're going to look at subgradient method and proximal gradient and understand exactly the answer to all of the questions that we've put down so far. We're going to move far beyond just two-dimensional problems that we can draw, but it's important to use these things to give us motivation and to seed for us what are the right kinds of questions to ask, as hopefully we've illustrated. What is the right step size? Why does one method perform better than the next? And we'll begin tackling all of these in the next session.